the lecture. And the second half of the lecture on Monday, March 26th, the day after break, we will talk about the intermediate reports for your project. Okay, so these intermediate reports will be due noon through Canvas on Monday. Okay, so I want you to finish them like enough time before class, not right before class, but enough time before class, so that you can have them like some copies printed out and to bring them into class. And so we're going to kind of pair you up in this class, or I think in groups. Your groups are going to form into sets of 3 groups each. Or we might get some pairs of 2, and you're going to discuss amongst yourselves about what you've done so far on the project, just to give you some peer feedback, to see what other groups are doing, and to kind of get more feedback on this. There's also an email that was, or not email, an announcement on Canvas that was posted by TA Sunipa about signing up for meeting with me to do kind of a 5-minute review of your project in class. Okay, so there are 43 projects or something like that, so I'm going to meet with each of you for about 5 minutes. I found that actually this 5-minute meeting is actually kind of, for most groups, that's about the right amount of time. Some groups, it'd be good to have a little bit more, and then we can find time to meet a little bit more, but I'd like to meet in person with each of the groups. And so there are times either after class Monday or Wednesday, or sometimes on Tuesday as well. I'm kind of eating into my my day when I set aside for research and don't have meetings, so I have time to meet all of you guys. So how many groups have already signed up for a slot? Great. Okay, so if you haven't done so, there's still plenty left. But please sign up for those slots. And when you come to that meeting, you should bring a printout. What's easiest for me, bring a printout of all the parts you've turned in so far. So bring your proposal, your data collection report, and your intermediate report. And in that 5 minutes, I will for the first rough minute, I will read everything that you've done very briefly, and then we will kind of discuss for about 4 minutes on kind of what's going on. And if you have other charts or something you want to show me, you can bring those as well. Okay? And there's, if it takes a little bit more, there's a little slack built into the schedule. But and if you can't meet on any of those slots, email Sunipa, and she'll help set up some other time. Okay, so any questions on what's going on so far? So what should you do for the intermediate project report? Right? Have people started writing up this report yet? You're about 2 weeks away from this. Right? So kind of the point of this report is so that, well, one is that I want you to not do everything for the whole project in the last kind of week before it's due, right? So that's one of my main goals. And I think the projects are much, much better if you have these goals that are going on in between. Some stuff, it may just take a long time to run something, or you may need to wait on something to finish. So if you don't start it soon enough, you're just not going to have time. Even if it doesn't take that much actual work time, it may take computer time. The other reason is that this is a good chance for you to kind of get some basic stuff working, and kind of one of the things you should bring to me with this report is kind of a sense of a plan or questions of how to complete the project, right? To say, here are the things left we think we should do to complete it, or we're not sure what's left to do to kind of make this a good project. We've done some stuff, we're not sure how to evaluate what we're done kind of is successful or not, right? So my goal will be to kind of inform you on how to kind of finish up what you need to do for the project to make it as complete as possible. Okay, so if you haven't kind of done much yet on the project, this won't be very helpful. I won't be able to give you any meaningful feedback, right? Other than, you need to keep working harder, right? So I'm not asking for complete projects, but I'm asking for kind of some basic prototype stuff to see if the basic idea you're trying to do is going to work or not, or you need to kind of do a major shift, right? This is kind of the last chance to make a decision of we really need to change focus, right? So kind of make sure something's working, so I can give you good feedback, or we can decide if you need to kind of either do a large shift, or maybe a 10% shift one way or another from what you initially expected. Okay? Yep. And if you can't make it here for any reason, for you on the camera, feel free to contact me. We can try something over Skype or something like that. All right. I think that's good. Okay, so in the next 2 lectures, so this one and the next one, we're going to talk about a cool phenomena that has to do with when you have really high-dimensional data, but the signal or the model that you're trying to find is not too high-dimensional, meaning there's something very simple about the data, but you have lots and lots of features or lots of measurements. Okay, and so to kind of set this up, so I'm going to initially talk about this kind of idealized and simple version of the compressed sensing problem. Okay, and this will be there are more complex versions of this, which we won't really get into. And then I'll talk about today the simplest algorithm that works most of the time to actually kind of recover these simple sparse signals, called orthogonal matching pursuit. And then on Wednesday, we'll talk about how to apply this to a version of regression. And this will be this, on Wednesday, we'll talk about this lasso version of regression, which biases you towards sparse solutions, and we'll basically see how to kind of take these ideas and apply them to these a little bit more relevant regression problems. Okay, so to start this out, I kind of have some sample-ish data up here, and the way to kind of look at this is we're going to have a signal, and this will be a vector S. Okay, and this is S transpose. We'll write it as a column vector, but it's just a string of bits. Okay, and so what's interesting about this is that this is supposed to be sparse. Okay, so the length of this signal, so S is going to be in our D, and in this case, D equals 32. But if you notice, it's all bits, so it's all zeros and ones. But it's mainly going to be, much more ones than zeros. Okay, and this is about the smallest example I can put up where you can start to see kind of what's going on. But in general, we're going to be much higher dimensions. Could be thousands of dimensions here. Okay, and I'll kind of give some context, but let me kind of walk through this mechanical kind of what these different components are first. Okay, and so then I'm going to have where I'm going to assume that there are only M. So there are only M of these 1 bits, and in this case, M is going to be equal to 8. In general, we're going to want to have M much less than D. Okay, so in the setting that this would be kind of useful, D is going to be thousands or millions, and M is going to be like maybe tens or hundreds. Right? So it's going to be much more dramatic in the situations where this is useful for. But here we have M equals 8. There are 8 1 bits. You can see them up there, and there are 32 different bits. So it's, in this case, it's only 1/4, but in practice it will be kind of, maybe this ratio is going to go to 0. If I write m over d, it's going to, as we get bigger and bigger, it's going to, this ratio is going to go to 0. It's not going to be a constant fraction even of the bits. It's going to be a really small number. Okay? And then what we're going to be looking at, they're going to be this signal out here that's sparse, and we want to basically find these 1 bits. So the goal is to find the 1 bits in S, and there's going to be, again, a small number of them. M is going to be something reasonable and small, and we want to find all of these 1 bits. But we're not going to see S exactly. We're not going to get a full view of S. We're going to get these kind of these random aggregated views of S. Okay? So, and that's going to be this Y. So this Y is going to be, this is going to be a random aggregated view of S. Okay? And in particular, Y we're going to get as the dot product with the random, so with the random measurement. This is a random so measurement. And in particular, each xij, so the j'th element of this xi vector, and xi is indexed by I because I'm going to make multiple of these measurements. So each of these is going to be uniform and random from -1, 0, and +1. Okay, so I'm going to, each of the bits, each of the values in xi, each of the elements is randomly a -1, a 0, or a +1. Right, so that's this string here. This is also of length 32. It's the same as d. So, and then xi is again going to be in -1, 0, +1 to the power d. So it's a length d vector made up of these objects. Okay? And so we can design this random measurement. This is something we essentially choose, but it's going to need to be random, and I'll try and explain why this is. But we can choose this. We can choose this random measurement xi, but then we only observe the dot product between s and xi, which is yi. We only observe this dot product. Okay, and so if you take the dot product, remember the dot product is the sum of the element-wise products of the elements, right? So it's 0 times -1 gets you 0. 1 times 0 gets you 0, right? So if I get a 0, which I get in 1/3 of the measurements, and I get in most of the S values, then I'm going to contribute to the sum of 0. Okay, but then I'm going to add up all of these things, and there are some of them which are positive, right? I'm going to have some positive ones here. And I'm going to have some of these which are going to be negative, right? And I take the sum, there are 4 positive, 2 negative, and the sum is going to be +2. Okay? So I'm going to get a bunch of these measurements. Okay? And so the claim is I'm going to be able to recover S. So the claim is I can recover S exactly with only basically n equals k, which is going to be a constant, times m log of d over m of these measurements. Okay, so this is m log d over m. This k is a constant. k is going to be somewhere between 4 and 20. And the size of the constant will be determined by how long we're willing to spend to try and recover this. Okay, if the data sets are very big, they're big enough that there's some scale things taken into account, and we're willing to spend a very expensive algorithm to do this recovery, we can drive this down to about 4. If the data sets are not huge, and we're using orthogonal matching pursuit, maybe we can only guarantee that this is going to be 20. Okay, but let's say it's 4. Let's say we're in the big setting, it's 4, so we're basically 4 times the number of 1 bits, which is way, way smaller than the number of total bits, times some extra log factors. Okay, and the log factors here, this basically just tells us, if you think about this is information needed in order to tell us the location of those bits. Right? If I were to tell you where the bit is, I'd have to kind of store a number that's of length log of d to tell you the index of the bit. Now it turns out, it's log of d over m, so this is a little bit better. And it turns out you can actually encode them a little bit better. You only need to store the gap. Right? If I store this gap, and then this gap, and then this gap to each of those bits, I only need this much space to store them on average. Right, so this is basically the space just needed to store this data, and I have a small constant factor in front. So I can find all the 1 bits by just doing these random measurements on this data. Okay, and each one random measurement looks like a dot product with the data. Okay, let me try and give an example where this comes up. And this example is not exactly how they do it in practice, but this will kind of illustrate what's going on. Or I'll give a few examples of these. So, of compressed sensing. Okay, so the first example, and this was something that kind of made this, kind of started people as a tangible thing people could get their hand on, which was called a single pixel, so a single pixel camera. Okay, right? So how does a camera typically work? So a camera typically works is that there's some cat that you're trying to take some picture of. It looks kind of cute. It's playing with some ball of yarn, right? And so then the camera kind of has this frame of view, and so it says, okay, to capture what's going on with this cat, I'm going to try and get kind of some notion of what's going on in each of these pixels. Each pixel I'm going to color in, right? So each pixel maps to either a black and white value or three color channels, right? Cameras nowadays are doing some more complex stuff, but in essence, it might take multiple frames, but in essence, this is what's going on. And so how this works is that there's some view which is going through a lens, right, and is mapping to something in the back of the camera, and then the camera has this array of these light sensors, and each of them corresponds with one of these pixels. Right? If you set the lens up properly and you focus it, then you get the things at the right distance will map this one-to-one with each of these pixels in these light sensors in the back of the camera. Okay? And so how many, if you shoot something in RAW on a camera, a fancy camera nowadays, how many pixels do you think there are? So I think it's like in the millions somewhere, right? So let's say, so you said maybe this is 40 some million of these pixels. Okay, but most cameras do not store all these pixels anymore, or you have to even fancy ones, you have to turn on a setting so it stores it in RAW, in this RAW format. And then if you want to do more manipulations afterwards, sometimes it's better to work in this RAW. But typically what it does instead is it converts this into a JPEG. And it does this in hardware, right? This used to be something, you know, when cameras were first coming out, before they were in phones, this was often done in software, and people said, well, in phones, we're doing this all the time. They built special purpose hardware, so before it even goes to the memory of the phone, so it stores in space there, it converts it into a JPEG, and it's doing some compression on this image. Okay, and then it stores in this JPEG, and then maybe it compresses it further. If you send it in an email, or you upload it to Instagram, it might be doing some further compression. Okay, and so what you end up seeing is going to be a much more compressed version of this. Right, and that's because, you know, what is this compression doing? Well, maybe there are a set of pixels which all have roughly the same color in them. So I can just say, okay, all these pixels have the same color value, so I'm just going to describe a color and then list all the pixels that have this color, right? Or I can kind of group pixels together and say there's some sort of effect going on. There are lots of different compression techniques going on. But your eye really cannot distinguish these 40 million different pixels. If you zoom in far enough, you'll eventually start to see them, but for most of what you see on your phones or, you know, browsing through Instagram or something like that, you aren't seeing all these pixels, right? So can you compress them? Okay, so this is typically what's done, and so they had this idea, can we somehow do the compression at the sensing step? While we're gathering this information, can we build some cheaper sensor, some way that does the compression before we compress it into a JPEG, right? So that we don't, or maybe if we have the same number of pixels, we can get a higher resolution thing of that's going on with the same number of pixels. Okay, this is kind of the inverse of what they're doing. So the single pixel camera instead maps all of this down, right, the sensor down to a single light sensor, right? So this is now one light sensor in the back of the camera. But in this mapping part here, it's going to introduce, so there's some thing here that this is going to randomly mix stuff up, right? So instead of just going to one sensor, I just get gray every time I see it. If I just average everything, so what it does instead is a random mask. Okay, instead of in this example where my measurement was -1, 0, and +1s, this random mask is each, it still thinks of them as each pixel, but each pixel is now going to be a 0 or 1. Okay, the nice thing about the math, as we'll see here, is that on average, each pixel is going to be 0, unless there's a signal, because this is on average 0. This is, on average, is not 0, so you have to do some extra correction here, but it can be done offline afterwards. Okay. So it's doing a random mask. Instead of taking one measurement, it's going to then take a bunch of measurements rapidly in a row and hope that whatever you're taking a picture of is not moving too much. Okay, and so it's a still picture and so forth, and they actually, I think they initially did this in a simulation, so they had a raw image, and then they did this so it was fixed. But then they took these random masks where each pixel is a 0 or 1, and then they averaged them together. And the averaging together is just this dot product. Then you need to divide through by something, right? So it's essentially the same thing as going on here. And then they got all these random masks put together, and they try and recover this original image. Okay, so this worked I would say, it's kind of okay. All right, so you could do this, and you can kind of see roughly what they're taking the picture of, but it was not as good as a typical camera. Okay, so there's some error in the process here. Now notice this is harder, right? In this problem, we're trying to recover just 0, 1 bits. In this case, we need to get a grayscale for each of the pixel values. So this is a harder problem. Maybe not grayscale, but color, and so you would get the color a little bit off, but they would get the sense that there was something dark there, something like that. So it didn't quite work, but I mean, they got something working, which is super cool, that they could build a camera this way, taking random mass of the whole image and then kind of combining them together. Right? So this was kind of a demonstration of proof of concept. This has found uses in a few other places. I've heard that the Hubble Space Telescope uses some version of this. And I don't know exactly what it's using or if it's still doing this, but the idea is the Hubble Space Telescope is this telescope that's in orbit. Most telescopes are on Earth, and so they have all this atmospheric stuff they have to, noise they have to deal with. This is it's on a satellite. It's a big telescope, but it's expensive to send signals back and forth. So if we know the measurement vector ahead of time, and we take these compressed images of stuff, and then we just send back the result of the dot products, that the communication is going to be much less. You could also think of it as you're taking a big picture of the sky, and only in certain spots are there stars and galaxies out there. So I just need to recover, is there a star or galaxy in each of these spots? I just need to recover the 1 bits. So there's something like that going on. Someplace else this occurs, and this is probably more with the regression version, but this is one of the major kind of success stories, early success stories of this. If you ever get one of these, if you get like a head injury or something, you get these, you get like an MRI on your head. And if you've ever had to do this, it means you lay down this machine and you have to sit perfectly still, and it takes like half an hour to get a really good imaging of what's going on based how the technology works. And the more you move, the stuff gets jumbled up. They take kind of these projection views of your head from different angles, and they each take a while to do, and they need many of these views to be able to recover what's going on. And if you move, then these become not aligned. So, with most adults, it's hard for them to sit still so long, but if you have kids, you know that it's hard to get kids to sit still for even half that long. So can you get a pretty good image of what's going on in the head in significantly less time? I'm willing to compromise a lot on the resolution now if I can cut down the amount of time that the kid needs to sit still. Right? And so these MRIs are taking these measurements of the brain from different angles and using much fewer of them and getting kind of some reasonable pictures on kids that otherwise I wouldn't get enough data to be able to recover the whole thing. Okay, and it's using some version of this compressed sensing framework. Okay? And so these are kind of some situations where this is coming up. And again, this is an idealized setting of what's going on. We'll see kind of we'll use basically the same mechanisms to do this for very high dimensional regression. You'll kind of see it today, and then we'll go through it more formally on Wednesday. Okay. This kind of you kind of buy that this is an interesting problem. Yeah.
So like in your example in the previous slide, the end result was 2 because you added everything together.
Yeah.
I kind of don't really see how you can go from 2 back to where the 1s were.
Right, okay, so this is one measurement. Remember, I'm going to be doing a bunch of these measurements, and we'll see how to do this, okay? So, yeah, so that's what we're going to do right now. Okay. Page. All right, so, the input here now is, so I'm going to talk about the orthogonal, so matching, orthogonal matching pursuit algorithm. And so the input is going to be a measurement, so matrix now, X, okay? And X is going to be equal to a stacking of these rows, X1, X2, up to Xn, okay? Remember that n was going to be equal to some constant times m log of, where this was d over m. And I kind of have to guess what the right value is. I assume they're not going to be more than some number of n bits. Okay? And each of xi, recall, is going to be -1, 0, +1 to the power d. Right? So this is going to be an n by d matrix here. Okay? And what I'm going to also see is I'm going to get this vector y, which is going to be equal to it's going to be x times s. Okay, s in this case is going to be a vector, x is a matrix, right? And y is going to be so y is going to be in Rn. So I'm going to have n of these measurements, right? Each one is going to be like 2. y1, yi will be like 2. So I'm not just going to have all of them, but I'm going to I'm not just going to have one, I'm going to have all of these. Okay, and so now my goal is to guess which of the bits in S, so I know S is dimension D, which of the bits are likely to be interesting here. And so how I'm going to do it is I'm going to, so the key step is I'm going to choose so the column xj, so this is not a row, it's a column, right? So I'm going to use kind of an uppercase x, the column, and lowercase, so you can roughly tell by the size. I'll use j to index the columns and I to index the rows. So I want to find the column, which is going to be arg max of, say, xj prime, and x out of all the columns which maximizes y dot product xj prime, the absolute value of this. Okay, so basically this dot product is basically telling me how correlated is the column with this observation vector that I see. Right? How correlated is a column with an observation vector? Yeah.
Will you describe the prime versus just xj?
Yeah, so just to distinguish that they're both indexing columns, and this is, I'm considering all j primes, and this is the one which maximizes this. So it's an arg max. So if I just take a max, it returns the value. If I do an arg max, it returns the element of the set which maximizes this. Yeah, so good question. Just notational kind of, this is the notation that's commonly used. Yeah.
So the elements in x are drawn from -1, 0, and 1.
Correct.
If you're correlated with y, your value is still going to be really close to 0.
We'll go through an example and we'll see that we want to have a column which, when y is large, xj is also, the corresponding row in xj is also large. So it's going to be 1. It's going to be a 1 when like xji, so the ith row of this column vector is going to be a 1 typically when the yi is going to be a large value. When the yi is going to be a small value, could be negative, then this will often be a -1, have a -1 in that element. Okay? So this is, right, so we're going to, so the key insight here is that we're going to do this, and then we're going to estimate this gamma value, which is the arg min of gamma in R, or in general in -1, or in 1, or maybe in 0, 1. Like, we can often set this to 1, but just kind of the general case here. So that y minus xj gamma. So I want to minimize this. Okay, so I want to find some value here, and if I'm in the binary case, this has to be a 1. It's either a 1 or a 0, because this is going to correspond with our guess of the bit in the jth part of the signal S. Okay, so if I draw a picture here, when I do this, draw it up here, I've got this X matrix here. I'm going to get out this Y, and I'm going to have as input S. Right? So S is going to have these 0, 1 bits. Right? So if there's a 1 bit here, then it's going to activate everything in this column of X. Everything in this column of X is going to be added up into the vector Y. Right? So if there's a 1 bit in this element of S, then it's going to, all the positive things in X are going to be added onto Y, and all the negative things are going to be subtracted. So that means that if I look at this column Xj, this is Xj, this is Sj. If I look at, so this is, and this is kind of saying gamma is our guess at Sj, the jth bit here. So I'm trying to say, if this is a 1, and I multiply by xj, so I use the bits in xj and I subtract those from y, is that better than saying this is 0? Do I get kind of a smaller representation of y, this observation vector, if I assume there's a 1 bit here than if I assume there is a 0 bit? I think that's, initially we assume that all the bits of S are 0, and then we say, can I explain what happened with y if I assume this is a 1 bit? Or in general, I can try and fit some continuous value to this. Right? But the guarantees of getting it exactly will usually be around if I have 0, 1 bits. But we'll see we can get some continuous values on Wednesday. Yeah.
So what we're trying to do is we are first trying to find out what is the best dimension, and then we are trying to find out what is the best value that particular dimension can take.
Yeah, right. And for now, we're going to assume it's just a 0. Let's say this is a 0 or 1. Right? I don't know. Okay, so you could read, but let's say it's the basic assumption was a 0, but if I said it with a 1, is that going to be a better fit? And the one that's the argmax of this is the one that's going to be most correlated with it. It's going to be large when this is large. It's going to be small. If they're both negative, then I get a positive value here. If they're both positive, I get a positive value. If one's negative, the other is positive, then I get a negative value. That's anti-correlation. That's bad. If I get a 0, it doesn't do anything. Right? So if I get more than not, these are both positive or both negative, then setting a 1 bit aids this explanation, and I can shrink y by I can shrink y here. So then if I do this, then I update y is going to be equal to y minus xj gamma, and I set sj equals to 1, or is equal to gamma. Right, so I'm going to basically set that jth bit of s to be gamma, which maybe is a 1, and then I subtract out this effect from y. I have a residual left over, and then I kind of keep pumping this through. So then I've explained part of what happened in y, and I'd like to get y to be all zeros. If y is all zeros, then that means that I've got all the 1 bits and the rest are zeros that go through and don't do anything. Right? I kind of expect on average it to be 0, but there's some deviation from it. And I want to uncover where that deviation came from. So I want to drive this to 0, and if I can explain part of it away, then I'll drive this down to 0. And I just repeat this process.
So does this mean that I have some pre-knowledge of x?
Yeah, so you know what x is part of your input. Your input is x, which is generated randomly, and is y. Right, so the input here, the input is x and y. But I don't have s, and the goal is to recover s. Okay, I wrote this out a little bit more clear. Maybe this is more clear, so you can see this is wrapped inside of a for loop, and now what's useful to see here is I can think of R as a residual vector of what's going on. Okay, so this is kind of a leftover of explanation of what's going on here. Okay, and so then I find the column, which is I think is going to be the best explanation. I'd solve argmin for gamma, maybe it has to be 0 or 1, maybe it can be real. And then I update this residual. And this is gamma j, I'll set this to 0 or 0 otherwise. Okay, let's try and go through an example, and then we can kind of discuss some more aspects of this. Okay, so let's try and run it in this setting here. Okay, so D here is going to be, let's see, D is going to be 8, and M is going to be 3. Okay, so this is a pretty small example, and this is really too small to expect it to work. I'm going to have ties, and I'm going to arbitrarily pick some things, but knowing kind of what we know, so that I'll always pick the ones that end up working. Okay, just so we can see it happen. Otherwise, it's kind of it's going to be too big to really see what's going on. Okay. Okay, so the first step is to find the column which is the largest dot product with y. Yeah.
Shouldn't D be 10?
D is good. 10. Yeah, just miscounted. Great. Thanks. Okay. That's all right. So we're going to find the column which is the largest dot product with y, and let's just kind of go through these. Let's say y x1. The dot product is going to be, so I'm going to get the first 3 rows don't matter because I hit them with the 0. Then 1 and plus 1, 1 and minus 1, those cancel out. And I get a minus 2 and a 0. This one's going to be 0. Right, so the dot product here is 0. If I do the dot product of, right, so that's going to be, I'll just write it down here, this dot product is 0. This one's also 0, right? The first 3 columns or elements of y are 0, and the last 3 of x2 is 0. Right, for 3, I'm going to get minus 1. What? 1. Okay, good. yeah, you guys help me out. So in this next one, I'm going to get 2, right? So I get a -2 and a -2, right? And then this one, I'm going to get a 3, right? That's for x5, right? For 4, I'm going to get a 1. For this one, I'm going to get a minus, let's see, that's -2 plus, minus, this is 2. I take the absolute value, right? So absolute value of -2 is 2, right? Right? And then, so this is absolute value of the dot product, right? And then this is going to be, is this -3 or 3? That's a 3. 1, this is going to be 4, right? 4, and then, and this is 0. Okay? Good. Okay, so the largest one, so we're going to say that arg max of xj prime of absolute value of y xj prime is going to be equal, this is going to be x9, right? It's going to be this column here. Okay, so I'm going to assume that there's a 1 bit. Oh, look here. There was a 1 bit up there that worked. Okay, so I'm going to set, so I'll set S9 equals to 1, and I'm going to set my residual equals to y minus xj prime times 1, right? Times 1, okay? And so this is going to be equal, my new residual is going to be 0 minus -1, that's going to be +1, 0 minus 0, 0 minus 0, 1 minus 0 is going to be 0. Okay, so I started out with 0, 0, 0, 1, now I'm at 1, 0, 0, 0, 0. I haven't gained anything yet. And then I'm going to have a 1 minus 1, another 0, and then a -2 minus -1, get to a -1 here. Right? So this, from the original y vector to this new residual y vector, this is kind of simpler. I had a total of kind of the L1 norm of this one, for instance, was 4. I had 1 distance away in the 4th coordinate, another one in the 5th, and then 2 in the 6th coordinate. Now I'm down to 1 in the 1st coordinate and 1 in the 6th coordinate. And notice that it's moved where the air is. I've kind of moved, it's like whack-a-mole a little bit. You knock down air here, it pops up a little bit somewhere else, but hopefully, on the whole, the number of moles are kind of eventually kind of not popping up as much. Okay? Okay, good. So this was 1 round. Let's try this again. Let's try this with, now I want to find equals arg max xj prime of, let's call this R1 times xj prime. Okay, so which column is going to be the best now? The first column here is going to be 0. Second column is going to be 1. Third column is going to be 2. Right, with R, right? I get a 1 with the 1 and a -1 with the 1. I only need to look at the top and the bottom coordinates now because I've already zeroed out a lot of it. Right, so then I'm going to get 0, 0, 0, 0, 1, 0, and 0. Ah, cool. So now I'm going to say the third one has the largest value. So I'm going to say that this is going to be x3. x3 is the argmax. Lo and behold, there is a 1 bit up there. This worked again. It's not always going to work. Right? It's not always going to work, but I think I must have set this one up. Okay? That's what, you can set up some bad examples, but if you do them all day long, you guys are just going to be like, okay, find whatever, right? So it's magical when it works though, right? Okay, so I found x3, and now I need to, I'm going to set, means I can set s3 equals to 1, and now I'm going to set, let's do it over here, r2 is going to be r1 minus xj prime, which was x3 times 1, and this is going to give me, well, I've zeroed out this coordinate and also the last two coordinates, but unfortunately, some errors popped up someplace else. Okay, so now I've got a -1 and a 1 here. Okay, so I didn't really make much progress, but I don't know, I feel like that was still good somehow. Like I found one of these 1 bits. Okay, but I haven't completely solved this here. Okay, so I still have some information left in this residual, but I did the best I could at that step. Okay, so let's do this one more round, and let's do the dot products with this new R2 vector. So now I want to find the R max xj prime of R2 xj prime this. Okay? Let's figure out what we're going to get here. So I only need to look at the middle 2 bits, and I'm going to get a 0, 1, you get 2, okay? I'm going to get a 1, 0, 2, 2, 2, 1, and 1. Okay, so this is less ideal. Now I have some ties, if I did all that correctly. Okay, so this would happen. This is why it's not going to work on small sizes. You're going to get ties like this. You have to break them arbitrarily. Okay, on large data sets, you may get ties too, and hopefully each of the ties is going to be a 1 bit. So if I choose x3, I'm going to go back to where I was before, right? I think the ideal thing would be to set it. It turns out that the setting gamma in this arc bit would be actually, if I could choose between 0, 1, and -1, the best thing would be a -1 would set it back to where it was before. Or a 0 would do, it's not going to really do anything. It turns out if I choose, what is this going to be? x7, which is, this is x7, this is x8, and this is x6.
So are columns 3, 7, and 8 supposed to be 0 instead of 2?
Let's see.
Oh wait, never mind. I see it.
Yeah, so it's going to be, I'm taking the absolute value.
Okay.
Now, I think what's happening is actually it's going to be, now if I take the absolute value, it's mean I'm going to need to set this to be a -1 here. And so I guess in the general case where you might fit other than 0, 1 bits, you want to consider the absolute value, but in this case I can only be positive. So I think I don't need the absolute value. In which case those would be -2s. And then those would be small. Right? And I wouldn't want to take them. Right. Yeah, so if I can choose x7 or x8, and those will kind of zero out these 2 bits, but they'll add stuff elsewhere. If I choose x6, right, this is the simplest column, right? If I choose, right, I can do x3, x6, x7, x8, and if I choose x6, then I can set this new residual R3 is equal to R2 minus x6 times 1, right? And this is going to be the all zeros vector. Right? And lo and behold, there's a 1 bit here. Okay? So kind of cool, right? So it worked in this example if your numbers are big enough so that the randomness starts to kind of, you get these concentration bounds start happening, then what's going to happen is if you have a 1 bit in the signal, all of the pluses and minus ones are going to kind of, there are going to be enough of them that they're going to, in aggregate, have an effect on Y, and you'll be able to pull this out. But if they're small enough, you're going to get some weird ties and some other stuff going on like this. Yeah.
So here, how did you break the tie? You just chose this one? Or
Yeah, I chose this one. There's, in general, if you get a tie, something might go wrong.
Could you do something where like you choose whichever one will lead to the least error? So like compute the R and for all of them, and then the one that has the least error, just go with that one.
Yep. Yeah, so that would make sense to do. Have like, you know, if you look at this algorithm, have a look ahead. Say if there's a tie, take whichever one gives you the best solution here. That's a very reasonable thing to do, right? In general, you would apply this and you hope there's usually not a tie, but this doesn't work, and basically you need the constant in the number of rows you need higher so that so then you get kind of more random trials so that the signal shows through is more likely to show through. And so you're less likely to get ties, but it might happen. Right? This is going to be one of the things that with some probability, this is going to actually recover the solution exactly. Yeah.
So for your observation, is there, for any given data set, a specific way in which you're supposed to obtain that?
So is there any, then you're supposed to set this matrix?
Yeah, so you get your measurement, and then with your observation there, is that usually just given to you, or like how?
Yeah.
How do you obtain that?
So what's going to happen is like this Y vector is going to be a bunch of these single pixel aggregate readings I get. I'm going to do it n times. I'm going to take an aggregate reading, or I'm going to take measurements at a random angle in an MRI machine, and I'm going to I'm going to get these aggregate signals, and then I need to kind of put them back together. And I'm going to know what the measurement matrix is, right? So I can do this recovery procedure, but I'm not going to know what S is. I'm passing it through this kind of randomly aggregating filter. Yeah.
Why do you want the all zero vector, and why do you want it to be null zero?
It basically means that I've explained the signal. So, you know, the all zero vectors implies that if I do that, this implies so R3 equals 0, 0, 0, 0 implies that Y, which is the original observation, is going to be equal to x9 plus x3 plus x6. Exactly. It's exactly equal to the sum of those three columns. Now, I want to try and recover my observation, right? I want to kind of find what this observation, explain how did I get this observation. Now, it could be that there are some settings where I'm going to say, plus some noise, right? So that I'm going to have a little bit of observation left, but I'm going to attribute that to some noise, and I'm going to say that's okay, right? So I want to explain as much of the observation as I can every step, right? And if I get down to where Y is very small, and I can say, okay, that part's just noise, I can stop. That's some other settings when I'm not going to assume I get the exact measurement procedure here. I'll say I just want to make y small in some sense, some 1 norm, some L2 norm, some sense, and say the rest is attributed to noise, and this is my explanation. And it's a much simpler explanation than a length 10 vector. I just have three pieces. Does that help? Yeah.
So how does this, okay, so since we do have to still store like at least n things, or with respect to n, then how does that compare to just storing the spaces between the ones and getting like an instant prediction?
The spaces between the
ones in S.
Well, yeah, I could store that as well, right? And the most compact way of storing this is not to store 3, 6, and 9, but to store 3, and then a gap is 2, and then another gap of 2 gets me to 9, and then I stop. And that would be slightly more compact if these are enormous bit vectors. But you know, I'm happy. I mean, this isn't that much more, right? On these data sizes, it's more convenient to work with this. There's some things like much of the indexes of the web, they store the kind of the web addresses as the difference between them. They sort them and store them that way, and that becomes much more efficient because these are so big and they're so complex that at that point it pays off. Actually, that speeds up searching by big orders of magnitude if you do all this correctly. There are going to be settings where the signal is so big, D is billions and billions, that I really want to store the gaps because I'm going to really compress it. But on the setting of millions, it's not going to make that big of a difference.
So when the matrix gets larger, so why would there be like less conflicts, or why would there will be like less ties?
Yeah, so why are there going to be less ties as I scale this up? Okay, so what's going to happen is that so if I look at a random column, let's say a random column that corresponds with the 0-bit in S. Okay, it's going to tend to be on sometimes 1, sometimes 0, sometimes minus 1s, right? And now I could re-choose that random column after I run the experiment, and it's not going to change anything about y, right? So assume that it was chosen afterwards. Okay. Now if I take the dot product between y and this random column, each term in that dot product in expectation is 0, right? Let's try. Okay, so I have to look at the expectation of y xj such that s of j equals to 0. Okay, so the y values, let me assume that these are all, they could be negative, they could be positive, but I can push this expectation through. I can say that this is equal to the sum over I equals 1 to d of the expectation of yi times xji. Right? And the yi is a given constant, so this is equal to yi times the expectation of xji. And this expectation of xji is 0. Right? So this is equal to the sum equals yi times 0, which is 0. Right? So if I pick a column such that Sj is equal to 0, the expectation of this inner product is going to be 0. Right? And so that, but if it's not equal to 0, it's going to be tend to be correlated. Right? Let's just, yeah, and it's a little bit hard to see that it's going to be exactly what it's going to be, but it's not going to be equal to 0 because it'll depend on what the other values of y are going to be. So each element of y in expectation itself is going to be 0, but it's going to have a variance to it. So some of them will be further away from 0 than others, and the ones that are further away are going to tend to correspond with xij values that have the same sign. Does this help make a little more sense? Okay. Okay, a few other remarks I wanted to make about this. So, oh yeah. So okay. So there are a couple of optimizations that we can do here. So optimizations. And the first one we're going to explore on Wednesday. Instead of saying xj is equal to the arg min of xj prime of essentially, so I can essentially do r minus xj prime gamma, oh wait, sorry. So I set gamma equals to this, right? So this is how I was saying I was setting gamma before. So after I found the column, I can look at this, find the gamma which minimizes this. It turns out that it's going to be a little bit better to do to have a regularizer term where I try and bias towards having a sparser value of gamma. Like gamma here is, and in this case is a scalar, so let me just write gamma. Okay, so I'm biasing toward having a sparser version of gamma. Okay, and this is going to correspond with this like lasso version of a regression that's going to bias towards sparser parameters. And if I set this this alpha parameter, right, then and I have noise in the data, right? So if I don't, my observations are not perfect, they have noise in them. Then if I set alpha to be a little bit, the larger I set it, at some point it's going to say, you know, you'd rather off having gamma 0 than to try and fit some of the noise. Some of these columns are just going to correspond randomly with the noise, and you're going to tend to set those. But if I set alpha a little bit larger, at some point I'll say, you know, you're better off just to keep gamma as 0 instead of setting it to a positive value. And we'll kind of see why this is on Wednesday. Okay? And the other thing, so this is kind of which goes with this, is that, oh yeah, and this is not xj, this is going to be sj, right, to set this as this gamma value. Okay, so this, to set the jth bit this way. Okay, instead I can think of, instead of solving for, I want to solve for gamma, or I want to solve for the set gamma 1, gamma 2, up to gamma, let's say t, for on the tth step here. I want to try and set, I want to consider setting the old values I chose over again. Instead of optimizing just on the one bit, I want to kind of, on the tth step, consider setting all of the t bits I've decided to look at so far. Okay, so this is going to be, now I'm going to go back to the original value of y, and I'm going to look at the here I'm going to say let's call this S equals 1 up to T, where these are the things I found in the S step, xjs times gamma js, right? So I'm going to consider trying to set all of these at the same time. So this is really a much smaller version of the problem. This is going to be at each step, it's going to be a t-dimensional version of least squares regression. Okay, I'm only looking at these t coordinates that I picked out before. I picked out t minus 1 coordinates before. I find this tth one now has the most correlation with what I found. And now I'm going to try and reset all of those t values that I'd set as non-zero before. What this will allow me to sometimes do is I can sometimes recover so from a mistake. I may have made a mistake earlier where I set a bit 1 that should not have been set 1. Okay, so this will allow me to go back and fix that. Okay, and because this formulation is exactly this least squares, I'm just fitting these coefficients here. I'm fitting t coefficients here, and t is going to be less than n in general here. So this is a well-formed least squares problem. Okay, and I can combine this with 1 by setting, by adding this regularizer on here, and I can take this gamma vector and put a 1 norm on this. And this will bias towards sparse S, or sparse gamma. So this will kind of bias towards setting some of the coefficients to be 0. Even if they're going to have some correlation, they're going to tend to set them to 0 if they don't have a lot of correlation. And this is what Wednesday's lecture will be about. Okay, so this is going to be a bit more expensive. If you remember, there was not really a closed form solution if I put the L1 regularizer on here. If I put the L2 regularizer, it was ridge regression, and there was a closed form solution for it again. And so sometimes what people do when they're kind of a little bit lazy, but tends to work in practice, is instead do alpha times, put a regularizer on gamma L2, so then instead do this, then do the trick for ridge regression, where there's a closed form solution, and then round the gamma j s to 0 if small enough. Okay, so if coefficients are small enough, maybe I snap them to 0. Okay, and this is kind of a shortcut. We'll see on Wednesday that you can actually work with this. It's feasible to do. It's a little bit more painful, but you can work with it. And then if this is big enough that you actually don't want to do the matrix inverse, which is required for this step, you can plug this into a stochastic gradient descent solver. And then this one is not, using the L1 regularizer is not that much harder than using the L2 version. All right. Okay, so I think that's roughly all I want to say. If you have any questions, I can take in the last couple minutes. Otherwise, if you didn't see at the beginning of class, I want you to, we'll have kind of an ethics-y discussion on p-values and p-hacking. And so there's a paper to read here. And it's like 17 pages, so if you don't read all of it, that's fine. But kind of, if you get a chance to read through this, it's well written, and it's not mathematical. If you can at least read through the second page, you'll get a sense of what it's about. And then it's just a case study where it goes through kind of some examples like this throughout the rest of the paper. Okay, and the conclusion section might be interesting. But then, if you don't get everything that's in here, I'll spend a few minutes setting up all this stuff up in class on Wednesday. All right, great. I'll see you in a couple days. We'll have the quizzes to return on Wednesday as well. They'll be here before class and after class as well. Good?
I wrote a lot of